Weak bases are only kinda good proton acceptors, just like weak acids are only kinda good proton donors. The equation for a weak base when it comes to equilibrium studies always has the weak base and water on the reactant side, and the conjugate acid and the hydroxide ion on the product side. Just like we wrote an equilibrium constant expression for weak acids, starting with a Ka value, we can write an equilibrium constant expression for weak bases using the symbol Kb. Notice that we have the conjugate acid and the hydroxide ion in the numerator, as we would expect, but we only have the weak base in the denominator, and that's because, as you recall, we don't include pure solids or pure liquids in an equilibrium constant expression, and water here is a liquid. So it is going to appear in the equation, but it does not appear in the equilibrium constant expression. Typically, weak bases are nitrogen-containing molecules, which sometimes we call amines, or they're also anions. All of these have lone electron pairs which accept protons. And here's an example. We have here on the left a weak base. It happens to contain nitrogen, and you can see it's got an unshared pair there, and that unshared pair is a negative center of charge, and you might imagine that a positive proton would be quite happy to click right in there. And sure enough, if you look on the right side, if you look on the product side, there is the proton that has docked, you might say, into the weak base, forming the conjugate acid. And the water molecule has now been transformed into a hydroxide ion. Turns out that this weak base in the lower left corner has the name methylamine, which played a prominent role in this TV series that is kind of related to chemistry, but in a very dark way, called Breaking Bad. So let's try a problem. What is the equilibrium concentration of ammonia in a solution of pH 9.35 if ammonia's Kb is 1.8 times 10 to the negative fifth? First, we need to know that ammonia's formula is NH3, and then we need to write the equation for ammonia acting as a weak base. Here it is. There's ammonia. We also know that we have to write plus water. Then the ammonia is going to gain an H+. It's going to gain a proton, which will turn it into the ammonium ion. That H+ will have popped off of this water, which leaves it as a hydroxide ion afterwards. Okay, so far so good. We're going to now skip a little bit. If you are writing any of this down, leave a little bit of space because we're going to put some ice-like calculations right underneath this equation. We're given in the problem that the pH is 9.35, which means the pOH is 4.65, because recall that the sum of those two must be equal to 14 at 25 degrees Celsius. And then if we take 10 to the negative pOH, we can calculate the hydroxide ion concentration at equilibrium. That means that we know the value of the hydroxide ion concentration at equilibrium, 2.24 times 10 to the negative fifth, and we also know the concentration of the ammonium ion. Think about if we were doing an ice calculation on the right side here, on the product side, wouldn't it say 0 plus x, and over here 0 plus x? Well, we know what x is. That's why we've substituted 2.24 times 10 to the negative fifth in both of these two places. Of course, we don't care about water. That is totally irrelevant. And for the ammonia concentration, we have the initial ammonia concentration, but then it drops by this amount, which is, of course, why we have the pH that we have. We want to know what the equilibrium concentration is, so we need to find X and then put it into this expression that I've put a red oval around, and that will be our equilibrium concentration of ammonia. There's our Kb, 1.8 times 10 to the negative fifth. We've got products in the numerator, reactants in the denominator. This is not a quadratic. We can solve it for X fairly easily. I trust that you can do that. 5.0 times 10 to the negative fifth. Again, what we're asked is, what's the equilibrium concentration of ammonia? This 5.0 number is the initial concentration of ammonia. So what we need to do is take 5.0 times 10 to the negative fifth and look at the red oval, subtract off 2.24 times 10 to the negative fifth, and that'll give us our equilibrium concentration of ammonia. Let's summarize weak bases. Just as weak acids are kind of good proton donors, weak bases are kind of good proton acceptors. Weak bases usually are species having a lone pair of electrons, and it is this lone pair that is the docking point for an accepted proton. The reaction equation for a substance acting as a weak base always has two reactants, the base and water, and two products, the conjugate acid and the hydroxide ion. And you can see I've put that equation, that general form, right here, 2/3 of the way down the slide. The equilibrium constant expression for a weak base has this form, shown in the lower right. Notice I put a couple of stars by this water. The water appears in the equation. It does not appear in the equilibrium constant expression.